Hello everyone, I am Dr. Krishna Sarker, Department of Electrical Engineering. Here in this session, I will be going to discuss about types of transfer function with poles and zeros concepts. This is linear control systems, lecture series on linear control systems, lecture number 12. So our new topics, types of transfer function with poles and zeros concepts. Then overview. What is transfer function? Then general transfer function, different types of transfer function with respect to paths and loops. Number one, forward path transfer function, feedback path transfer function, open loop transfer function, closed loop transfer function, or overall transfer function. Then different types of transfer function with respect to number of poles and zeros. With respect to number of poles and zeros, the transfer function mainly three types. Proper transfer function, PTF, improper transfer function, IPTF, and strictly proper transfer function, SPTF. Then another overview with respect to decomposition technique, transfer function mainly four types. Signal flow graph transfer function method, direct decomposition transfer function method, cascade decomposition transfer function method, parallel decomposition transfer function method, and another form, canonical form. The transfer functions are mainly four types. Again, number one, observable canonical form or second companion form. Number two, controllable canonical form or first companion form, diagonal canonical form transfer function techniques, and this is the very important Jordan canonical transfer function techniques. Another concept, poles and zeros of a transfer functions, and impulse response and transfer functions. So these are all overview or targets or focus in this session. Then what is transfer function? Already discussed in previous lecture, Laplace transform of output divided by Laplace transform of input provided all initial conditions are zeros is called transfer functions. So this is the definition of the transfer function. The transfer function of a control systems is defined as the ratio of the Laplace transform of the output variable. This is also called response or effect to the Laplace transform of the input variables. This is also called excitation or cause, assuming that all the initial conditions to be zero. So what is the definition? Ratio of the, this is the very important part, ratio of the Laplace transform of the output variables to the Laplace transform of the input variables. And this first part, this is the output. So this section actually effect, and this section cause. Input section or excitation section, this is the cause. So cause effect, actually this is the cause effect, and this part, all the initial conditions to be zero. This is also very important for transfer function definition. Then symbolic form, transfer function. What is transfer function? Transfer function equals to Laplace transform of output divided by Laplace transform of input. Output means effects and input means excitation or cause, and provided all initial conditions to be zero or all initial conditions are zeros. Another forms, transfer function equals to Laplace transform of output divided by Laplace transform of input, and Laplace transform of input variables or excitation. This is also called cause, and this is the response or effects. All the initial conditions are zeros. So this is the definition of transfer functions. Then forward path transfer function. What is forward path transfer function? This is the block diagram, closed loop block diagram or feedback. This is the feedback path. That's why this is feedback path or feedback block diagram. This section, reference input or set point, this is represent R of S, and this is the comparator or summing point. This is also called regulator, and next this signal is called actuating signals or error signals. This is E of S, and this is the control elements and control systems, and the gain of the control elements or control systems is G of S, and output of the G of S is the controlled output. This is the controlled output. So this is the reference input, this is the control output, this is the control system gain, and this section actuating signal or error signals, and this is the feedback path. This is the feedback path, and feedback element or measurement equivalent to H of S, and this is the feedback signal, and B of S is called primary feedback signals. B of S is called primary feedback signals, and these feedback signals may be positive, may be negative, may be positive, may be negative. So this is the block diagram of a feedback control systems. Then forward path transfer function, FPTF. What is forward path transfer function? This is the forward path. Just this section, input section, and corresponding then operation, and after operation this is the output. So this is the forward path, and this forward path transfer function equals to G of S. G of S means gain, control elements gain, or this is the transfer function equivalent to C of S, controlled output divided by actuating signals or error signals. So what is the forward path transfer function? This is the G of S. This is the G of S. That means controlled elements and control systems gain, and C of S, controlled output or effects, and this is the actuating signals or error signal E of S. So forward path transfer function equals to output by input, because this is the output and this is the input for control element or control system. So output by input ratio is called transfer function. That's why G of S equals to C of S by H of S, and provided all initial conditions to be 0. Then feedback path transfer function. Already discussed this figure. This is the block diagram for feedback control systems. Feedback path. So this is the feedback path. This is the feedback path. What is the transfer function for this feedback path? What is the transfer function? In this case, this input, this is the input, this is the input. Again, this is the input section, and this is equivalent to C of S. And after operation, this is the feedback B of S, or this is the output B of S. So H of S equals to what? This is the measuring element. Output equals to B of S divided by C of S, because transfer function equivalent to, this is the transfer function, H of S equals to B of S output and C of S input. Output by input is called transfer function, and all initial conditions will be 0. So this is the definition. Feedback path H of S equals to B of S divided by C of S, and all initial conditions to be 0. H S equals to measuring element gain, and B of S equals to primary feedback gain, and C of S equals to control gain and control output gain. Then open loop transfer function, but this is the very important problem, because open loop means not input with respect to input with input block and output. This is with respect to closed loop system. So open loop transfer function with respect to closed loop. This is the closed loop system or feedback system. Calculate open loop transfer function with respect to feedback. In this section, open loop transfer function OLTF ratio of the output of the feedback path B of S. This is the B of S to the actuating signals or error signal E of S for any given feedback loop. So what is the open loop transfer function? Open loop transfer function equals to ultimate B of S. This is the B of S primary feedback gain. B of S divided by what? Divided by actuating signals or error signal E of S. This by this. B of S divided by E of S is called open loop transfer function. This is also equivalent to C of S divided by E of S into B of S divided by C of S. If C of S cancel, then B of S divided by E of S again return. So this is equivalent to C of S divided by E of S equals to what? C of S equals to output, E of S equals to input. C of S equals to output and E of S equals to input. So for this forward path, G of S, C of S divided by E of S equals to G of S. And another section, B of S divided by C of S. B of S, this is the B of S output divided by C of S. So output B of S divided by C of S equals to H of S. So this is equivalent to H of S. So open loop transfer function for a closed loop systems equals to G of S into H of S. G of S into H of S is called the open loop transfer function. And this is called open loop transfer function, G of S into H of S. Then overall transfer function. What is overall transfer function? Again, this is the total block diagram, and total block diagram overall output equals to C of S and reference input equals to R of S. So CS by RS is called the overall transfer function. So what is the overall transfer function? Overall transfer function equals to C of S divided by R of S equals to what? The forward feedback gain G of S divided by 1 plus G of S into H of S. It's called forward path, is called open loop transfer function. So C of S divided by R of S, overall output divided by reference input equals to G of S divided by 1 plus G of S, H of S, where G of S equals to control system gain and HS equals to measurement or feedback element gained. When H of S equals to 1, that means feedback path gain equals to 1, then CS by RS equals to GS by 1 plus only GS when HS equals to 1. This is very important, and this forward path is called the unity feedback forward path, and this is equivalent to 1 plus G of S, 1 plus G of S. And in this section, 1 plus G of S, HS, 1 plus G of S, H of S is called the characteristic equation. If this section equals to 0, then this is the called characteristics equation. 1 plus G of S, H of S equals to 0 is called characteristics equation, and this characteristics equation gives the stability of the systems or poles location or poles roots of the roots, also gives the roots of the systems. And when all the poles and zeros left hand side of the S-plane, suppose this is the real axis RE, real axis, and this is the imaginary axis. This is left hand side and this is the right hand side. And if all the poles denoted by cross and zero denoted by 0, all the poles and zeros left hand side of the S plane, then system will be stable. This is called the overall transfer function of the systems. So what is transfer function? Suppose this is the control systems gain G of T and reference input or set point R of T, and the output equals to C of T. This is a system in time domain. In time domain, after operation, then this will be R of S, reference input, because R of t, Laplace transform of R of t equivalent to R of S. Laplace transform of C of t equivalent to C of S, and Laplace transform of Z of t equivalent to Z of S. So this is equivalent to, and R of S equals to frequency domain input, and G of S system gain transfer function, and C of S equals to overall transfer function. This is the Laplace domain and frequency domain, where S is equal to sigma. S is equal to what? S is equal to sigma plus j omega. Sigma is called the real part, and omega is called the imaginary part, and sigma, unit of sigma equals to Newton, and unit of omega equals to rad per second. In this section, G of S equals to what? G of S equals to CS by RS. So this is the gain G of S of transfer function G of S equals to overall output C of S divided by input R of S. So this is called the transfer function. This is called the transfer function output. This is the output, this section, and this section is the input. So output by input is called transfer function, even if all the initial conditions are zeros. If all the initial conditions are to be zeros. And this is equivalent to NS divided by D of S. What is NS? NS is called numerator polynomials, and DS is called the denominator polynomials. And numerator gives zeros of the system, ZDROS, ZDROS, zeros of the systems, and denominator gives the poles of the system, POLES, poles of the systems. So NS order gives the total number of zeros. So numerator gives the total number of zeros, and denominator gives the total number of poles. This is the D of S order gives the total number of poles. If, this is the assumption, or this is the very important section, if P greater than Z. So what is the conclusion? Numerator, denominator poles, numerator zeros. If P greater than zeros, P greater than zeros means number of poles greater than number of zeros. The transfer function is called the strictly proper transfer functions. This is called the strictly proper transfer function. If poles, POLES, poles greater than zeros. If poles greater than zeros, then this is called strictly proper transfer function. And if P less than Z, that means number of poles greater than number, that means number of zeros greater than number of poles, the transfer function is called the improper transfer function. Improper transfer function. If P equals to Z, that means number of poles equals to number of zeros, the function or the transfer function is called the proper transfer function. This is called the proper transfer function. In this case, NS one polynomial, denominator also polynomials, and number of powers, NS power and DS power is equals. So if P equals to Z, the transfer function is called the proper transfer function. Then improper transfer function. What is improper transfer function? From general transfer function, this is the general transfer function equation. CS by R of S is called the transfer function, where numerator is called the N of S, and this is also called the zeros of the systems, and this is the poles of the systems or denominator of the system. So numerator powers equals to M and denominator powers equals to N. So what is the transfer function transfer function? B0 s to the power M plus B1 s to the power M minus 1 plus B2 s to the power M minus 2 plus ... Bm, and s to the power N plus A1 s to the power N minus 1 plus A2 s to the power N minus 2 plus ... plus An minus 2 s square plus An minus 1s plus An. In this case, numerator and denominator powers not equals. So if M greater than N, M greater than N's, that means if M greater than N's, numerator power greater than denominator power. The transfer function is called the improper transfer function. Improper transfer function, if the order of the numerator polynomial is greater than the order of the denominator polynomial, the transfer function is called improper transfer function. What is the example? Number of zeros equals to 2. In this case, s plus 1 equals to 0, 1 whole square equals to 0, the s is equal to minus 1, another value also s is equal to minus 1. This is the zeros position, and s is equal to 0 is the poles position. That means origin. This is the origin, position, origin, because s is equal to 0 at origin. Then here, number of poles less than number of zeros, or p less than or z greater than p. So z, number of z equals to, in this case, 2, and number of poles equals to 1. So the above transfer function having the simple poles s is equal to 0. In this case, the pole position s is equal to zeros, and the zeros position s is equal to minus 1, s is equal to minus n. And what is the pole 0 location? What is the pole 0 concept? Suppose this is the real axis, this is the real axis, and this is the imaginary axis. Then put this pole first, s is equal to 0. This is the s is equal to 0 position, one poles at s is equal to 0, and another section, this is the 0 position, s minus 1. This is the 0 position, s is equal to minus 1, s is equal to minus 1, and another 0, s is equal to minus 1. So red section, second zeros. So this is the s is equal to minus 1 position. So this is the pole 0 location. In this case, 2 zeros left hand side of the s plane and 1 poles are at origin. This is the and next, strictly proper transfer function. What is the strictly proper transfer function? From general transfer function, this is the general transfer function. Already discussed this transfer function, where b0, b1, b2, b3, bm are coefficients of the s, and a1, a2, a3, an also coefficients of the s. If m less than n, then that means denominator power greater than numerator powers, n power greater with respect to m. This is called the strictly proper transfer function. This is called the strictly proper transfer function. If the order of the numerator polynomial is less than the order of the denominator polynomial, the transfer function is called the strictly proper transfer function. And this is the example of the strictly proper transfer function. In this case, only one zero at s is equal to minus 5. At s is equal to minus 5, only 1 0, and s is equal to 0, 1 0, 1 poles, s is equal to minus 3, another poles, and s is equal to minus 6, minus 6, minus 6, minus 6, another multiple poles. That means in this case multiple poles. So number of poles equals to 4. Number of poles equals to 4, and number of zeros equals to 1. So p greater than z. This is the p greater than z, or denominator power greater than numerator power. So this type of system is called strictly proper transfer function. What is the example? Cs by Rs equals to 100 into s plus 5, s into s plus 3, s plus 6 whole square. Then calculation. Here, number of zeros less than number of poles, so p greater than zeros. The above transfer function having the simple poles at s is equal to 0, at one poles at s is equal to 0. Another poles s is equal to -3, and multiple poles s is equal to -6, multiple poles 1 zeros at s is equal to 5. So what is the pole 0 plot? This is the real axis and this is the imaginary axis. So put first s is equal to 0 poles, s is equal to 0 position poles. This is the s is equal to 0 position poles. So this is complete. Then next, another poles s is equal to -3 and multiple poles s is equal to -6. One poles s is equal to -6, another poles s is equal to -6. So this is the multiple poles s is equal to -6, -6. This is the pole 0 plot configuration. And 1 zeros at s is equal to -5. 1 zeros and the position s is equal to -5. Then proper transfer function. What is the definition? This is the general block diagram. If this is case number 3, if numerator power equals to denominator power, that means m equals to n, the transfer function is called the proper transfer function. If the order of the numerator polynomial is equals to the order of the denominator polynomial, the transfer function is called the proper transfer function. In this case, number of zeros, numerator means zeros, number of zeros equals to 4 and denominator also 4 zeros. So this is the m equals to n, and this transfer function is called proper transfer function. And in this case, p equals to z. And what is the 0 and pole position? Pole position s is equal to 0. First pole s is equal to 0. Second pole s is equal to -3. And third and fourth pole, multiple poles is equal to -6, -6. And what is the 0 position? S is equal to -5. This is 1 zeros. And another zeros, s is equal to -1, -1, -1. 3 0 in this case. So what is the plot of the pole 0 configuration for proper transfer function? This is the real axis and this is the imaginary axis. So put first origin s is equal to 0. This is the pole location and this is denoted by cross. Another poles s is equal to -3. This is the s is equal to -3 position, and multiple poles s is equal to -6, 1, and another poles also s is equal to -6. So this the pole 0 plot on this type of transfer function is called proper transfer function. And what is the 0 location? But first s is equal to -1, -1, and -1. So this is the one, s is equal to -1. Another 0 s is equal to -5, and second pole again s is equal to third pole. This is the this is third 0. This is third 0. So another zeros. This is the another 0. So 0 location s is equal to -1, -1, -1, -1, -1, -1, and 1 another zeros s is equal to -5. Then general transfer function. What is the general transfer function? The transfer function concept. This is the systems and gain system. Gain equals to GS, input equals to RS, and output equals to CS. So consider the block diagram of a simple linear systems shown in figure. The only assumption made concerning these systems is that the input and output are related to a linear differential equation whose coefficients are constant and can be written in the form. So first, this is the input section, this is the output section, and the output are related by the linear differential equation. Suppose the operation part inductance. What is the definition? L into dit dt. So this is the differentiation part. Similarly, C into dVdt for capacitor. So differential equation form the output with coefficients are constant, and coefficients constant, that means, and can be written as, suppose this is the differential equation for output section. This is the differential equation for output section, C of S, and this is the time domain CT, C of t into an plus an minus 1 dct by dt, d2 ct by dt2, an minus 2, similarly a2 d to the power n minus 2 ct, d to the power n minus 2 dot d to the power n ct by dn. This is the output equation, and these output equations, this is the position of the output. Inverse Laplace of CS is ct, and then this is the velocity of the output, dct by dt. This is the acceleration of the output. Then what is the input section? Suppose input equals to R of S, or inverse Laplace R of S equals to R of t. So RT equals to position of the input, and then dRT by dt equals to velocity of, and d2RT by dt2 acceleration, and b0, b1, b2 dot bm minus 1 bm are coefficients of the system. This is the which coefficients are constant and can be written as this form. So this is the general transfer function. Then taking Laplace transform both sides, and we get zero assumption. We get, this is the first, this is for first equation. Suppose C of S, Laplace transform of CT. This CT, this CT, this CT, this CT. Laplace transform of CT equivalent to C of S. So this is complete. Again, AN, this is the AN, and ddt equals to S. This is the ddt S, and this is the coefficient of ddt, or dct by dt. And next value, d2 dt square equivalent to s square, and coefficient an minus 2. This is the an minus 2, and dot similarly d to the power n dct by ct by dtn, and this is equivalent to s to the power n, and ct, this is the common part, c of t for first equation. Similarly for second equation, what is the Laplace output? This is the R of S, because this R of S, Laplace transform of ROT, this ROT, and this section ROT. Similarly, this is the ROT, this is the RT, this is the R of T. So this is the common part, R of S, and Bm constant. Similarly, Bm minus 1 also constant, and ddt of ddt equivalent to S, and RT equivalent to RS. Similarly, for second part, this is equivalent to S square, and this section constant part, and this is the RT equivalent to RS. Similar, B0 constant part, and d to the power m by dt2 equivalent to s to the power m. So this is the Laplace form of the differential equation. Then just divided CS by RS, calculate CS by RS ratio, and we get CS by RS equals to B0 s to the power m plus B1 s to the power m minus 1 plus B2 s to the power m minus 2 plus Bm minus 1 s to the power 1 plus Bm, and divide by s to the power n A1 s to the power n minus 1 plus A2 s to the power n minus 2 plus n. So this is the transfer function. Output by input, where output equals to C of S and input equals to R of S. Then CS by RS equals to, this is the polynomial equation, and this polynomial gives numerator side zeros of the systems and denominator side poles of the systems. This is also characteristics equation of the systems. And characteristics equation gives the system stability. Then general transfer function. The ratio CS by RS is called the transfer function of the element and completely characterize its performance considering the transfer function of the elements are G of S. Consider the general transfer function is this. This is already discussed. This is general transfer function. Generally m less than equals to n. In general transfer function, always n or poles s to the power n, that means denominator power always maximum or highest. So denominator power greater than numerator power. In this case, if m equals to n, the transfer function is this. So this is the transfer function, general transfer function. This is also called general transfer function. Therefore, assuming that the initial condition are 0, the Laplace transform of the output C of S equals to what? GS into R of S, because G of S equals to CS by RS. So output C of S equals to gain into reference input. In general, the function G of S is the ratio of the two polynomial in S, which is G of S equals to Z of S divided by P of S. The point at which the numerator polynomial Z of S equals to 0 and call the zeros of the system G of S. So this is the general transfer function concept. Again, general transfer function, a 0 is indicated by a small circle 0. The point at which the denominator polynomial P of S equals to 0 are called the poles of the systems G of S. Poles are indicated by a small cross x. So pole indicated x and 0 indicated by 0. At 0, the transfer function G of S becomes 0 and the poles it becomes infinity. The denominator polynomial for the transfer function is called the characteristics polynomial. Again, the roots of the characteristics equation 1 plus G of S, H of S are the poles and characterize the symbol behavior, system behavior. Then impulse response and transfer function. This is also very important for engineering students. Laplace transform or Laplace impulse response and transfer function. Laplace transform of an impulse function delta t is unity, always. This is also always. So G of S equals to CS by RS and CS equals to what? GS into R of S, GS into R of S. Then let us take the simple input R of t equals to delta t. R of t equals to delta t, and taking Laplace transform and we get R of t equivalent to R of S, and Laplace transform of R of t equals to Laplace transform of delta t equals to also 1. Then CS equals to only CS because R of t equals to 1. Then C of S equals to G of S. Taking inverse Laplace transform, we get C of t equals to inverse Laplace G of S equals to G of t. In this case, for an impulse input to system, impulse response C of S is equal to the transfer function G of S and all initial conditions to be 0. This is the impulse response and transfer function. And main point, when RS equals to 1, then CS equals to G of S. CS equals to G of S, overall output equivalent to system gain or planned gain. So thank you.